right, the purpose of this lecture is to go over two math formulas on the AP Bio exam that are for growth. So this is the ecology chapter. So the first formula I'm going to talk about is the formula for exponential growth. So what is exponential growth? Exponential growth is what it would be called if a population was growing unhindered, meaning at its maximum capacity. So you could see this perhaps in bacteria. At the very beginning, you have a couple of bacteria on a petri dish, and if there's nothing hindering those bacteria and they can reproduce every 20 minutes, then you're going to go, if you literally started with 1, in 20 minutes you'd have 2. Another 20 minutes it would be 4, 8, 16, 32. This would be exponential growth. And it forms on a graph what we would call a J-curve. It doesn't quite look like a letter J, but here's the idea. If you were to see a graph like this, and it doesn't have to be this steep, but you don't see anything leveling off, so the curve is just continually going up without doing this, without leveling, then that graph is representing exponential growth. Now, here's the thing. In nature, this really doesn't happen because the larger a population gets, you're going to have more individuals, right? And that means you're going to start to see what we call density-dependent factors. In other words, competition for food and mates and things like that. There's not going to be enough space to live. You're going to have accumulation of waste. There's probably going to be diseases. And this doesn't take into account predators and all sorts of other things. So realistically, this doesn't really exist in nature for very long. However, if a population was theoretically growing exponentially, there's some math we can do to calculate the growth rate and the size. So the first thing you need to understand, R max is the maximum growth rate. In other words, with no hindrances at all, this is the maximum rate at which a population would be growing. How would you calculate that? It would be the number of births minus the number of deaths in that particular generation over N. Now, what is N? N is your population size. So if we take the number of births minus the number of deaths over the size of the population, that's going to give us our growth rate per year. Now, again, if growth was exponential, that growth rate would stay the same year after year, but truthfully, that's probably not going to happen in nature. But let's just theoretically continue with this. So, the change in the size of a population over time, on the formula sheet for the AP exam, they showed this, delta N over delta T. In other words, the change in N, the size over a period of time, would be equal to the birth rate minus the death rate. Again, they don't really explain this, but the birth rate minus the death rate is basically this. The number of births minus the number of deaths over the size of the population. And that's going to give us R max. Now, the final equation, if we want to know how much a population will grow over a period of a generation, you would use this formula. So the change in population size over time, you're not actually plugging numbers in here. This is what you're solving for, is the change over time, would be R max, the growth rate, times the size of the population. Again, this is assuming that a population is growing at an exponential rate. Also, and this is important, the answer that you're going to get here is not going to be the size of the new population. The answer that you're going to get is basically going to be the number of new individuals you would expect. In other words, like the net increase in size. So let me show you what this looks like in action, so to speak. So a population of 100 has 20 births and 5 deaths. Let's start with what's the growth rate. So the growth rate for that population, if that's 20 births and 5 deaths per generation, would literally be births minus deaths over the size of our population, which is 100, and our growth rate, R max, would be 0.15. That would be R max. In other words, it's growing by 15% per generation. Now, notice this one, they want us to keep that growth rate. So they want us to use a growth rate or an R max of 1.5, or I'm sorry, 0.15, sorry about that. But they want you to do this if a population had 200 individuals. So, N is 200, R is 0.15, and you would literally do this. So you would say R max times N, so that's 0.15 times 200 individuals in the population, and a population exponentially growing at that growth rate, your answer that you're going to get here is 30. Now, that does not mean your new population size is 30. That means you're going to have 30 new individuals. That's going to be the net growth. In other words, the new population size would be 200 plus those additional 30, or 230. So be very careful, because this formula, R max times N, again, it's not going to actually give you the new size of the population. It's only going to give you the number of new individuals, and then you have to go back and add. Now, there is a slight shortcut that you can use on this, and I'll show you that on the next slide. So let's try a couple more problems. So another problem. Population size is 1,200. In year one, and when I say one year, let's just assume this is a generation. 720 births, 240 deaths, and they want to know the growth rate. So they're asking you for R max. That's going to be 720 over 240 times 1,200. Again, 720 minus 240 is just going to give us our difference in births and deaths. But if we're looking for the actual rate of growth, we would have to divide that by 1,200. So 720 minus 240 gives me 480. And if I divide that by 1,200, I get a growth rate of 0.4. So that is our R max, 0.4. Now, they want to know what will be the size of the population after I put a season here, and I apologize, I was inconsistent. I have year, then I use the word season, here I say year again. So let's just assume I was more consistent and I used the word generation each time. So after one generation, what will be the new population size? Now, technically, since you've already worked out this previous problem, you know by how many individuals it's going to grow. But if we didn't already know the actual births and deaths, and we were just going to use our formula, R max times N, then you would literally do 0.4 times my original population size of 1,200, and that's going to give you 480, which again, technically is the answer here if you just subtract. But they wouldn't do that on the AP exam, give you something where you would divide by N and then multiply by N again. Now, this is what I wanted to show you, shortcut. If population is growing exponentially, technically, and this is not on the formula sheet, if you do this, R max plus 1 times N, that will actually give you the new size after one generation. Instead of having to add 480 plus 1,200 here to get your population size of 1,680, in one step, R max plus 1, in other words, I would do 1.4 times 1,200, and in one step, I would get the same answer, 1,680. So if they just want to know the new population size, and they give you R max, and they give you N, formula sheet doesn't have it, but if you do R max plus 1 times N, that would save you a little bit of time. Now, tricky question here. It says, what would the size of the population be at the end of 3 years? Again, on the AP exam, I don't know that they would ask you for 3 generations, but they might ask you for 2 generations just to see that you don't make this mistake. Some people might think, oh, well, we just calculated that it's going to grow by 480 individuals per year. Not exactly. You calculated it was going to grow by 480 because that's 0.4 times 1,200. But in the second year, it's going to be 0.4 times 1,680. It's not going to grow by 480 individuals. In other words, if growth is exponential, it's growing by a rate. So to solve this the long way, so to speak, you would now have to, we now know after 1 year, we have 1,680. So to get after 2 years, we now have to multiply, and I'll use the shortcut. I'm going to multiply 1.4 times 1,680. And after 2 years, I would have 2,352 individuals, and they want 3 years. So now 1.4 again times that, so times 1.4, and now I actually get a decimal, but if I round to the nearest individual, the nearest whole number, I get 3293. So again, why would they give you a question like this? Because they would want you to understand that the population is not growing by a certain number of individuals per year. The population is growing at a particular rate. Now, there is a shortcut for this as well. And again, in reality, a population is probably not going to grow exponentially anyway, but let me show you on the next slide. Here is the 2 things I mentioned. So for exponential growth, if you do n times 1 plus R max, you would get the number in the next generation in 1 step. Also, if you do this formula, so if I want to know the size of a population, let's say in 3 years or 3 generations, like the previous problem, n was 1,200, 1 plus R max would have been 1.4. And I want to know the size of the population, what it'll be in 3 years. So for your exponent here, you just plug in how many years you want. So if I do 1.4 to the third power, I get 2.77. That doesn't really matter. Anyway, and if I multiply that times 1200, I get, guess what, the same answer, 3293. This is how many I would expect at the end of 3 years. Again, in reality, if you look up formulas online for ecology, you're going to see that this formula is not realistic because populations are not going to grow exponentially every year. But on the AP exam, if they ask you for exponential growth, this is the formula you're going to want to use. And if they asked you for multiple years and you could remember this little shortcut, it might be helpful for you. All right. Now, most populations are not going to grow exponentially, like I said. They're going to level off. And so that's what this graph is showing. So this is called logistic growth. What's going to happen is here, this is where all the density-dependent factors come into play, like competition and disease and waste accumulation and all that sort of stuff. And so what happens is the population starts off exponential, then it slows down, and it reaches what's called carrying capacity, which is represented by the letter K. And this is also something that can be numerically calculated. Carrying capacity is the maximum number of individuals that a particular environment can support. And this is something that could change. If it's a particularly good year, the carrying capacity might increase. Maybe there's more producers that year. If they come in and a bunch of loggers come in and chop down half of the forest, carrying capacity is going to drop. The real population, notice, is going to fluctuate around this carrying capacity. So a lot of times this will be shown as like a dotted line. Like this is, because if there's too many individuals, the next year probably you're going to have more deaths because there's not enough food to go around. But now if it's under, you're going to see it go up again. So it's going to fluctuate. So math for this. And here's a picture, exponential versus logistic. Oh, and this is called, by the way, an S-curve. J-curve, and this is an S-curve. All right, so the formula for carrying capacity is this. Logistic growth, it is R max times N times K minus N over K. So I'll do one problem with this just to show you. So if they were to say, and you would know because they're going to tell you on the AP exam it's exponential growth or they're going to give you a carrying capacity. So we have a population of 100, so that's N. R is 0.15, and there's no shortcut for this, by the way. So if I do 0.15 times 100 times, our carrying capacity is 110, times 110 minus 100 over 110. Make sure you divide by K. And this is going to tell you, again, by the net growth of the population. You actually get, when you work this out, about like 1.32, 1.36, something like that. Remember, that's not how many individuals you're going to have in the population. That's the net growth. So our original population was 100. And if I add to that my rounded 1, I would expect my population the following year to be 101. If it had been exponential growth, the size of my population would have been 115 because I would have just multiplied R max times my population size. Instead, because I'm close to my carrying capacity, and the closer it gets to the carrying capacity, the more this K minus N over K is going to slow things down. If K is 55, now our carrying capacity is actually smaller than the size of my population. So again, if I do my 0.15 times 100 times 55 minus 100 over 55, I'm actually going to get a negative number. I'm going to get about negative 12. In other words, right now my population is over its carrying capacity. So I would expect the following year that my population would actually go down. And I would expect maybe only around 88 the following year. So that's how you use these two formulas. And again, this second one is more realistic to what we would really see in nature. However, on the AP exam, they could ask you to calculate a growth rate. They could ask you, what would you expect if a population is growing exponentially? Or they could also ask you, what would you expect if a population is growing logistically, and they give you a carrying capacity. And again, it should be clear on the formula sheet. They have all of these variables labeled. And this could be a gridded question or possibly a free response or even a multiple choice. It could be really anywhere. So hopefully that tutorial helps you with the math.